Hi, my name is John Einberger. I'm Product Line Manager for Horizontal Machining Centers here at Makino. Today we're going to talk thread making. Before I do that, just a little bit of housekeeping. If you look on your screen, you'll see a Q&A section. The Q&A section is going to allow you to get questions to come into us so that we can address those live. We'll take a look at those questions as they come in today, and at the end of today's discussion, what we'll do is we'll address those questions on a one-by-one basis. With that said, I'd like to introduce Mr. Brian Baker. Brian is with us today from Walter Tools. Brian, welcome to Makino. Can you tell us a little bit about yourself, please?
Well, thanks for having me, John. My name is Brian Baker. I work at Walter Tools, and I've been there for about 15 years now. Currently, I am the product manager for all milling and threading products for North America.
Fantastic. Brian, again, welcome to Makino.
Thank you.
Today, let's talk about some different thread making methods. We're going to cover the gamut from tapping to thread forming to thread milling. And then as we go through those individual methods, what we'll do at the end, then let's do a comparison of them and see where they might fit into your manufacturing environment.
Sounds good.
So from a thread making, just from a generalized perspective, Brian, why is the correct thread making method and the choice of that, why is that so important in manufacturing?
There are quite a few methods of making threads that are out there. And depending upon what you're doing and the volume of the work pieces that you're putting out, and the value of the workpiece, having the right method that's going to give you a good, high-quality product and maintain the security of that, very important.
In a typical manufacturing environment, Brian, do you usually see people do a lot of value-added machining to a part before they ever get around to doing the threading operations?
That's a great point, and it's actually one of the key points of what we're going to be talking about today. The threading operations that happen on a part are usually the last thing that happens. Almost all the work's done. The turning's done, the milling's done, the holes are done, and then they put the threads in. And if they don't use the right method, that's the wrong time to scrap out a part.
Understood. Let's start out with tapping. Just a short video running here. Brian, if you could walk us through what we're looking at.
Okay. Well, right now, the picture that's on the screen is a spiral point tap for a through hole. But what we are looking at is a spiral flute tap, and we are cutting some material there, and we're actually generating chips and threading some holes.
So two different processes within the tapping family right off of the bat. When does the use of tapping to create threads make the most sense relative to maybe the other processes we'll talk about later today?
That's a great question. Tapping is generally one of the best known processes that are out there. Everybody's pretty familiar with tapping. And on most applications, it's a good process. When we get into some of the higher volume applications and some of the higher value applications, some of the other methods might come into play.
So for a job shop environment where maybe you're making 5 of these and 10 of those, the go-to generally, do you see an industry the go-to kind of revolves around that tapping process?
That's exactly what's going on there. Yes, I do.
All right, very good. Different styles of tools, different features, how do they come into play, Brian?
Well, first off, and when you're talking about cut taps, you're going to find 3 very distinct different types that are out there. The first one we're going to talk about is a spiral point tap. That's what we're looking at right now. The point of the tap actually has a little bit of an angle on there, and that's designed to take those chips, bind them together, and push them out the bottom of the hole. This spiral point tap is specifically designed and engineered for creating holes in a through-hole situation.
Okay, moving forward.
Next up, we are looking at a spiral flute tap. What we're looking at here is a standard right-hand helix. And when you're looking at a spiral flute tap, generally you're going to be using that for a blind hole. The spiral design that's in here is going to actually take these chips, lift them out and out of the hole.
So evacuate those chips, avoid that recutting, that part of the process. All right, and then the last one.
Straight flute tap. This is a very popular design out there. It works really well on materials that are very short chipping, crumbly like a cast iron or a high silicone aluminum. So using this tap in that application, you have a lot of advantages for the strength of it. It's a little bit stronger, and it can be used in both through and blind holes. But what we do look at here is in the blind hole situation, you're going to have to use some coolant to get those chips up and out of that hole.
Okay, so basically flush those guys right back out.
Yeah, we don't want to run into them.
Okay, understood. What other aspects come into play to keep that somebody should keep in mind for success in that tapping realm?
There's a couple of things that we really want to touch on. One is making sure we have the right tap for the right material. A tap that's used for hardened steel might not work very well. That's for a tap that's designed for aluminum. So as long as we're using the correct tap and the correct material and using the correct type of tap, spiral flute, spiral point, or a straight one in the correct application, we should be fine.
Sounds like a good conversation to have with a product manager when you're in doubt. So,
exactly. Hey, give us a call. We're here.
Understood. All right. Let's move forward to the next process, thread forming. Bit of a video here showing that process.
Yeah, with the coolant on, it's a little hard to see, but when we are thread forming, that is one of the most important things, is keeping it lubricated. Because we are taking material and we are pushing it around and pushing it into the form of a thread. So we're actually cold forming this material. But there's no cutting going on. There's no chips generated, but we're moving material around quite a bit. And if we don't have the proper lubricity, we can seize this up pretty quick.
So advantages of the thread forming, Brian?
Like I just touched on, the first thing is that there are no chips to deal with. All right. So we're not going to have bird nesting. We're not going to be filling up chip carts on here. And I've been in a lot of situations where people have cut their hands getting those chips off of here. That's gone. We are forming these threads, and by forming them, especially cold forming is what we're doing, we're going to compress that material and we're going to create a stronger thread. And in the process, it's also a little quicker.
Okay, so, very good. But what challenges and limitations exist with respect to thread forming versus the tapping that we talked about earlier?
Cut tapping is very universal, and we can almost cut tap in almost any material. But when we are looking at thread forming, we're going to be in a situation where not all materials can be formed.
Okay.
It has to be malleable. We have to be able to push that material into that form of a thread. And when actually what we're looking at right now, when we push that up into a form of a thread, it creates this volcano or fish mouth effect on the top here. That's very important, and it is normal. It is supposed to be there.
Okay. Implications of that from the standpoint of industry acceptance?
Very good question. This design with this fish mouth on top here will create a cavity where you can keep contaminants in there. Coolants, cleaning solutions, rust preventative, a lot of things that if we would use this type of forming, thread forming, in a food industry or a medical industry for implants, might not be very good. And it's not that we really can't get it clean, it's just that you can't prove you're getting it clean.
Any other limitations from the standpoint of where you might not be allowed to use it?
Yes, there is another really big one, and that's going to fall onto like the military aerospace applications. Please check with your end user if you can form thread those parts before doing it. There are some limitations that they have to make these parts out of a homogeneous piece of material, and cold forming it will violate that.
Kind of interesting as a side note, with my past experience here at Makino as a process engineer, we have actually seen the opposite around, where we've seen automotive part prints come out which specify specifically that thread forming must be used. I think what they're really after is the strength of that thread.
Exactly. That's one of the biggest advantages of thread forming, is that, yes, we are creating a stronger thread, but we're also creating it faster. And in the process, we're getting an increased tool life, too, out of these tools. Thread formers, in general, can last 4 to 10 times longer than a cut tap.
All right, moving forward, Brian, you'd already talked about the material requirement. It needs to be malleable. Any other commentary with respect to that material requirement?
Yeah, if you have like a crumbly cast iron or very high silicone aluminum that will actually crumble apart, a very short chipping material, there's a very good chance that that might not be a good candidate for thread forming.
Okay. Another aspect, power requirement. How does the power that needs to come from that machine spindle into the process, how does it compare for thread forming relative to the cut tapping?
We are significantly higher horsepower draw on a thread former. We are taking that material and we are forming it and we are pushing it around. We're not just cutting it. So you got to make sure, especially when you get into larger sizes, that you have enough horsepower in your machine and a strong enough tool holder to perform that operation.
Okay. So again, another great use of the product manager resource to be able to outline what that machine tool requirement is going to be.
Exactly. Yep.
Okay. All right. Brian, when does the use of thread forming make the most sense? If somebody's evaluating what process am I going to use to make this part?
Well, you said the key word earlier, and that's on some of these automotive parts. And that's where I see thread forming being the most applicable. High volume parts, a lot of the steels, the cast steels, and now the aluminums that are coming out in that automotive industry. When you're doing a high volume of threads and your cycle time is really dependent, thread forming is an excellent method of doing that. The cost per thread is very low.
Very good. Are there any other aspects to keep in mind, Brian, to get successful applications using thread forming?
Yes, there is. One of the most important things, though, is the hole size. All right. You would need to use a different core hole or tap drill for thread former than what we use for any other process that's out there. We are forming and we're pushing this material around. We need to use a larger drill for these. So you got to make sure you use the right tap drill. And the best place to find out where to get a good tap drill or the correct tap drill, ours is engraved right on the shank. Most premium tools will be something similar, very easy to find that information.
Yeah, so if you're thinking about experimenting a little bit in your shop, to Brian's point, just make sure you're using the right size drill to create that hole prior to the process that you select to make the threads.
Exactly.
All right, thank you. All right, let's move on to the third of the processes we're going to talk about today, Brian, thread milling.
Okay, what we see here is a conventional thread mill. This is what most people are familiar with, is this full thread length design, and it's a very universal tool. In addition to that, some of the newest style thread mills that we'll be seeing, or maybe even talking about, is this multi-row design. This is going to be a real revolutionary change for thread milling, and we'll touch on that in just a couple seconds here. Lastly, we have the orbital thread mills. This is a very great design, especially for small holes and deep lengths.
Yeah, that just from a reference standpoint, that's a 4 millimeter hole, pretty long L to D too, and you can see really very effective at creating those threads.
Yeah, I think that's 3.5 or 4 times D, and it's actually pretty quick. We're slowing it down on this one so you can see what it's doing.
So Brian, how does thread milling compare to both the tapping and the thread forming that we've already talked about?
It's closer to a tapping situation where we're actually cutting the material. So we are going to be cutting it and removing it from the workpiece. We're not forming it and pushing it around. The method is going to be a little bit different though. We're going to be milling it off of the part of the real small chips in an orbital sense of milling versus just a tap, which would go in and like create, one single long thread of, chips coming off of each flute.
So safer from that perspective.
It is.
A lot less probability of cutting hands, things of that nature. If somebody's not having to pull in this particular case, pull that bird's nest off of the tap.
That's a great point.
What about relative to thread forming?
Relative to thread forming, again, it is a different process. We are not forming the material. We are cutting it. So it's going to be in its own environment here, but it is a lot more universal. Thread milling can be performed on almost any material that's out there at almost any hardness. Right?
So Brian, what are the advantages of thread milling?
Well, what we just talked about was one of the biggest advantages, and that's being universal. Thread milling can be done in almost any material at almost any hardness. In addition to that, one of the biggest advantages of it is that if that thread mill would break, we can just pick that carbide out of there, blow that hole out, put another thread mill in, and keep on going.
So back to that really early discussion we had about that high value added part. Unfortunately, once in a while, the tools do break.
They do.
So it's easy to extract it and move on with life.
I'm seeing a big shift in the industry right now, especially in the aerospace, where you have very large, expensive components. We see a shift going where it's almost exclusively towards thread mills, just for that fact. At that end stage where we're putting the final threads in a part, you can't scrap out a part. You need the process security at that point.
Fully understood. How do you know what type of thread mill to choose for a given application?
It's really going to be based upon what that size is, your depth is, and your volume. If you're going to be doing a lot of thin, deep holes, that orbital thread mill that we just watched that video of is going to be the ideal situation for that. Short run situation, job shops, the conventional thread mill, that's your go-to. That skip tooth design, or the multi-row design as we like to call it, that is ideal for expensive parts, high volume parts. You can go a long time with very little radius corrections on that you can almost go like lights out machining with it.
Any other aspects, Brian, to keep in mind to have success using that thread milling process?
Making sure you pick a quality tool and you get the programming right. There's a lot of different strategies out there about whether we want to do conventional thread milling, climb milling process. Do we put a spring pass in there? Don't we? We, as an example, we have a software where you can put in your application and it'll suggest the correct thread mill and the correct process. And at the end of it, it'll actually give you the program too.
Okay, let's jump. Now, we covered all three of these: tapping, thread forming, thread milling. Let's do a point-by-point comparison. Let's take an attribute and discuss it relative to the three methods, starting with just the basics of the process.
Well, here we're looking at the basic process. Tapping and thread milling, they remove material from the hole. They are cutting material. Thread forming, we displace it. We're actually cold forming it and we're pushing that material around. No chips, no filled up chip cards.
Okay. Material use.
Again, tapping and the thread milling, they're very universal. We have taps that can go up to 68 Rockwell, and our thread mills can too. So the hardness isn't a limitation, or the malleability of the material is not. And thread forming, it is. In the right circumstance, it's a great tool, but there's some materials that just can't be used in.
All right. The industries and the applications where one or the other would or would not apply?
Exactly. Basically, almost back to that same thing. The tapping and the thread milling, very universal. They can be used across the board. But when you get to the thread forming, we touched on the medical, we touched on the food industries, and we touched a little bit on that aerospace, military applications where there may be some restrictions there for using that.
Okay. Thread strength?
Thread strength. Those formed, compressed threads are very hard and they're a lot stronger. So if you need a high quality thread, thread forming is going to be the one that gets you the strongest thread that you can get.
Okay. And again, drilled hole diameter, what do we start with?
Everybody's seen those tap drill charts, the charts, so you use this drill for this tap. Those apply for the taps, they apply for the thread mills together. But when you get to the thread former, we do need a different size drill. So just make sure you select the correct drill for that thread former that you use. And ours, for instance, you'll find that diameter engraved right on the shank.
And then the power requirement of the three processes compared.
The cutting processes generally are going to be a lot less horsepower required, whether it's the cut tap or the thread mill. But when we get to that thread former, we're pushing that material. We're forming that into that thread, and that takes a little bit of horsepower, especially when you get into the larger sizes. You may actually have to start looking to see it and make sure your machine has enough horsepower to create those large threads.
As a machining center product manager, what I would say is refer back to the power and the torque charts for that machine, for that spindle, and then look at that RPM that you're going to be running at. Make sure that you fall below those lines. Blind hole implications, Brian.
Or what you can do with when you're working with a tap, cut tap, or a thread former, they have a lead on them. They have to be able to get guided into that hole. And that lead, whether it be 2 threads or 3 threads of space there, that's your limitation about how close you can get to the bottom of the hole. With the thread mill, there's a full thread flush with the bottom of that thread mill. You can take that full thread all the way to the bottom of that hole. So,
all right. Any closing comments, Brian, before we close out today and move to the Q&A session?
No, not really. Just don't be afraid to give us a call. We either us or our software, we can tell you what the horsepower would be on those things, what the correct drill size is. We can get you your program. We can do whatever, we can to help you out with your thread milling, thread cutting, thread forming process.
Okay, very good. Brian, thank you for joining us today. Thank you to everybody out there for tuning in today. What we'll do now is transition to that Q&A section. Whatever questions you brought in, we'll address them on a one-by-one basis. Thank you. Brian, we have a couple of questions that have come in during the course of today's broadcast. Let me run those by you, and we'll go from there.
Sure. Sounds good.
Okay, first one that's come in. With the thread mills, you describe that as a safer solution to taps when it comes to breaking a tool in an expensive part. Can you explain that in a little bit more detail, please?
Sure. When a tap breaks off in a part, it's generally very hard to extract that. And it can actually damage that part and score up the top of the surface. Or when you do go through some of the processes to remove that broken tap, it could be semi destructive. You may have to melt that tap out or go into an elaborate process of milling it out with like a end mill or something. And very good chance you may damage that part. With a thread mill, when that is machining, if it happens to break, it's going to bounce off and like move away from the walls of the thread. It'll fall away. This is easily able to be extracted out. And when you get a brand new thread mill put into that tool holder and you touch it off, the distance to that first full thread is always going to be even. And when you put that tool back in the machine, you have a set start point and end point in the CNC program, and it's going to repeat. So you'll be able to jump in there, remachine that thread with that brand new thread mill, and you're going to have a part that's almost indistinguishable from, a regular hole that a tool did not break on.
So for those high value added parts, very little risk in using that thread mill operation with scrapping the part out at that point.
And even if you are in a rework situation, it is a lot faster than that process I described for getting a tap out of there. So you're definitely going to be saving time on that end as well.
Okay. All right. Moving on to the next question. With Walter being a European-based company, is everything that you offer, is it all metric shank, or is there a possibility of getting tooling with inch shank, or how do you handle that?
No, we're not exclusive to those metric shanks, which we call DIN taps. We have a very wide selection of taps and thread formers with the inch size shanks on them. And those are available in either ANSI or DIN ANSI construction, as well as a large selection of the DIN that you mentioned.
Okay.
But if people are actually looking for these, we have a brand new catalog out that is exclusively for the North American market, and everything in this catalog has those inch dimension shanks in it.
Kind of brings on a follow-on question. You're mentioning DIN and ANSI and even DIN ANSI. What is the difference between those designations?
It's a great question here. Historically, in the United States, North America, we've been exposed to ANSI taps. These are generally a shorter tap, these are the ones that have the inch-sized shanks on them that many people are used to using. Over in Europe, though, they adopted a different standard called DIN. These taps are a little bit longer, and they are based and built on a metric shank system. Over time, many manufacturers, end users, customers started liking the longer taps, but in that process, they didn't want to change all of their tool holders and collets over to the metric ones. So the DIN ANSI construction was introduced using the traditional inch-based ANSI shank, but now also using that longer DIN style length, thus becoming DIN ANSI. Over the last few decades, this has become a very, very popular construction of taps.
Is there an implication then that you can tap to different depths with that, basically with that setup that you just explained?
It's kind of a tricky one here. A lot of times it's due to the construction of the tap, but I'll just start this off saying that like on ANSI taps, and let's say for cut tapping, they are generally designed to go about 2.5 times deep. Some manufacturers maybe a little more, some a little less. But when you get to the DIN style taps, the longer, the European styles, those were always built under the assumption of going about 3 times deep. That's 3 times the diameter deep into the hole, creating threads. But in general, we always have to consider the material that we're tapping. You're going to be putting a lot of radial forces on these taps. So going 3 times deep in aluminum is going to put different forces on a tap than if we would try to go 3 times deep in, let's say, a hardened steel. So if look at the manufacturer's recommendations. If they say their tap's able to go 3 times deep, it should. I wouldn't try pushing farther past to like 3.5 times deep if it's not rated for that.
And let me close out with one more that's just come in. What about depth as it relates to thread forming?
So now thread forming, It's a little different, but for the most part, most thread formers can go about 3.5 times D. If you look at the ANSI ones, the ANSI are a little shorter, which will make them a little stiffer and a little stronger. They can handle that extra depth. The DIN ones are longer. They can do that as well. But once you are in a part engaged and you are actually forming that thread, it doesn't change how deeper. If you go deeper, those forces don't really change that much. You're still moving the same amount of material with the lead of that thread former at basically any distance you go. So that's why I say most of them are rated about 3.5 times D, and it's a very good rule of thumb to go by.
I lied to you, Brian. I got one more that just popped up. Is another advantage to thread milling multiple size threads with the same pitch? What would be your comment on that?
Excellent. In shops that I personally have worked in and shops that I've done some testing in, we've had parts like that. They were doing some M10 by 1 threads, and then on a port, they had an M30 by 1. Well, that by 1 is the same pitch. It's a 1 millimeter pitch. So yes, you can use that same thread mill to do any 1 millimeter pitch threads that are on that part. It's very handy, and that's a great idea. Or a great comment, yes.
Okay. All right. Well, we will end with that. And I want to say once again, thank you to everybody who tuned in today. Look for a follow-up email. You'll be getting contacted through the Makino system. And what we'll do is we'll provide you a link to a recording of today's event. You can watch it again. Feel free to pass it out to your colleagues, share it with your organization. And Brian, thank you also for joining us.
Oh, it's been an absolute pleasure. And I'd like to also thank everybody for stopping in and listening to me today. So thanks.
All right. Great. Thank you, folks.